And he will talk about integration of renewable energies, competition between storage, the power grid, and flexible demand. So there's a little change in topic.
Thank you. It on. So thank you very much for inviting me to give a lecture here on some of the work we are doing for renewable energies. Maybe a few remarks in the beginning. I think we have a lot of effort now these days in Germany to of course talk about renewables, to bring it back into the universities and to work on it. And I think one of the most interesting thing is that we, of course, just find out what you have found out within the last lectures, that there is, of course, a huge diversity of subjects which we have to tackle to some extent. I mean, we have to talk about resources, as we learned. We have to talk about maybe just the change of the climate. But we have also to talk about other issues which in the end turn out to be quite complex. And I think that's the whole response also of the people to new installations and so on. So we have, although we are in principle a pure technical university, we have started to think on how we can bring in more issues like acceptance, social issues into the university as well. And we have started a new school, Munich Center for Technology and Society. And just this semester, we did a first course actually with engineers, where we try to bring them some information about public participation. I'm not sure if this will be somehow successful, but I think in all these aspects that we see that people do participate in a certain way in a lot of issues these days, and at some point they have, of course, also to learn that they are responsible for the outcome. And I'm not so sure if in the energy field this is well known to everyone, and we have to see how we can, at least with our engineers, do a little bit better job on that. Before I start on my talk, I like to go with you through this picture, which you probably in a different way have seen these days already. It's just the development of the major primary energy carriers, the fossil primary energy carriers in the recent years. And I think what is extremely interesting about it is, of course, that everything is rising. I mean, that is something which is well known. But there is, of course, and that's something which we have seen in the last 10, 12 years, that there is a reverse in one of the trends. And this is the trend about coal. I mean, when I still remember, let's say till this time, roughly till this time here, you could find a lot of people who made out of this graph, they extended the graph through to the, let's say, 100 years, and they made fractions out of this, and then they showed that there is a decarbonization of primary energy. This story was true until the year 2000, roughly. And after that, we had a recarbonization of primary energy. That is actually something which we have to see, that a lot of the problems which we see these days with increasing prices and so on is actually solved by going back to coal. And if we look into some of the energy scenarios which were done by YASA or whoever, all of them had usually one scenario in their basket, which said that we will have a return to the 19th century in the 21st century, going back to coal. This is actually what we do see these days. And one of the problems, I think, that we face in a lot of discussions is, for example, still this extreme controversy between nuclear and renewables. I think we should somehow step a little bit back from that and see that this is actually the problem we are probably running into. And if we could get a little bit better idea on how to solve this, then we might have a certain share of nuclear, we might have a certain share of renewables. I will talk now only actually about renewables, because this is where I want to go into. But I will, at one point, I will also make a very small comment about nuclear as well. So I will also, this is part of the introduction, we have to see where are actually the problems with the renewables coming into the play. And here that's is a picture. Here this alpha is just a share of renewables of the demand, which is satisfied for a scenario. One scenario is actually, it's a scenario for Europe. I will go a little bit more in detail later into this scenario. The only important thing is here what you see, at some point some overproduction, which you cannot easily integrate into the network happens. And what you do see here, that it is a very big difference whether you have either a system which is only based on solar, then you will run much earlier into this overproduction, or if you have a system based on wind, then you will run later into this. Actually, we have to do it here because that's for a non-big grid, then you will run a little bit later into it. And if you have a mixture of both of photovoltaic and wind, it's even a little later. So you would come at around 50-60% if you have not a huge power grid. If you have a big power grid, you can actually shift that roughly 20% into the other direction. So you can maybe come up to something like 80% of renewables without major problems of integration if you have a huge grid. We come back to that, but I think that's very important that we have to see, okay, we have roughly 60% we get problems when we are in a system, let's say, of the size of Germany. 80% we get into problems when we have a system of the size of Europe. And that's, I think, the first message which I think I like to convey. For me, that whole story makes only sense if we find a very European answer to it. It's a huge pity, I think, that within this energy debate we're so national focused still, and having, of course, actually some problems with Europe as a whole, as a project. I think that could be one of the projects which might be more successful than the euro in the first place was. Maybe the euro becomes a success at some point. Well, I'm still quite. I'm always an optimistic person.
Could you explain what you mean by overproduction?
Overproduction is just. I'm sorry. It's just a very simple concept. You just take a demand curve and you take what wind and solar can supply to it, and if it's bigger than the demand curve, then it's overproduction.
Okay, so it doesn't have anything to do with the grid, like.
No. We come back to that in a minute.
It's the production not injected into the grid, right?
Yeah, it's a production which you have to throw away. Yeah.
Okay.
Yeah.
And that's electricity demand, not energy demand.
No, that's just electricity. Yeah. Okay. Now I want to focus here in my talk first on the electricity. Although I will talk a little bit later on about the connection of the two. So this is when we talk about the integration of renewables into the power system. So I think we are discussing these options here. So we can. This is which I started with, and where I like to go a little bit more into detail. I think we can build up supergrids. That would be a solution. It's, I think, a solution which is, of course, under the circumstances we see these days, not at all realistic. We see, I mean, if you just heard the most recent news from Germany that our Bavarian government sets some plans aside not to build some power lines, you see that it's extremely difficult to do things like that these days. It wasn't in the 70s. I still remember as a child I was living in a house, and 50 meters behind my house a 380 kV line was built. I liked it as a child because I had a telescope and I could order the sky through the new lines. But that was, no one protested, but today of course it would be a huge upheaval if something like that would be built so close to buildings. Nevertheless, it's a solution, and we should keep it in mind, and it solves, I think, a lot of problems. Then, of course, I will talk a little bit about storage, which is also a certain solution, but needs some problems. And then I will come to let's say, more exotic things, like power to heat, power to gas, which is a coupling of the sectors, which would solve some of the problems. And in the end, I will talk a little bit about smart grids, which is a big word, and I will cook this down to a few things where we are currently working on and how these could be solved. So the first thing is we are working on actually is on weather data. We would like, of course, to have your data on the changes from the meteorologists. So we have had some hard time actually to get all the data together. We have now a nice database which is actually based on this MERA reanalysis data, and we have now data sets for all parts of the world for wind, solar, precipitation, and so on and so on. It's roughly 30 years time span, and some of them are roughly in a 1 hour resolution. So it's a huge data set which we have collected, and where we work on, where we're a little bit proud on, because many people don't have, let's say, have time series over many years. Some are just working with 1 year, but if you work with the renewables, you see that you have to work really over many years, because the differences between the years really matter sometimes. If you, for example, make a study on storage, we just see that the seasonality of wind from 1 year to another is really changing. Sometimes we have a really seasonal, a winter, summer season variation, sometimes you don't. And if you plan a seasonal storage, it makes really difference which wind year you have taken. And therefore it's important to have a longer period of time. Okay, when we come now to the supergrid I like to talk about, we just take here 3 data sets. One is just a good wind location in the North Sea, one is Germany as a whole, and one is Europe. And we have, just by imagination, distributed a lot of wind turbines over this area and make we come back to a model in a minute just to see. And if you make now the wind duration curve out of it, the ordered wind duration curve, so you just order this by the magnitude, you see that there is really a qualitative difference between when you talk about one turbine, if you talk about Germany, and if you talk about Europe. Yeah, it really makes a difference, because here you have really a much smoother line, and if you look into the histogram, you really have all the time some power. It's not that you here and here you have always times when you have no power output, and in this scenario we have always some power coming from the wind turbine. So that's, I think, the first very important message. It's really making a difference if you go to larger structures. I mean, that's not our finding. There were many people who claimed that before, but I think we have to work harder on that to understand it, because it really makes things much simpler. And of course, the investments you have to do in the high voltage power grid, and also even the resources you need for that, is comparable lower than many other possibilities to solve it.
This is onshore.
This is mainly onshore, yes. Yeah. So now we take this. We have taken this and this data, and we made a model out of it. It's called ORBS. Actually, you see from the name that the model was first applied to cities. Not we have then extended it to power. And it was a study which we made, as you can see here, is a study we made for the Desert Tech initiative. So they asked us to make a study on what benefit would a large system have. And so we have here each country you see here was a node in this model. And we have really taken a greenfield approach, more or less a greenfield approach, and try to get an idea on what in the year 2050 could be there if we would reduce something like more or less all the CO2 emissions to maybe only 5% of the emissions in 1990, which is more or less necessary in the power system if you want to reach 80% in the overall reduction. And of course, we describe wind and PV really by hourly resolution. Of course, you have to make now a lot of assumption on what the electricity demand is. So we keep the electricity demand in Europe as it is. We increase it in the MENA region, of course. And then you have to make some assumptions about gas prices here. I haven't shown that, but okay, we assumed here that would be the prices for the investment costs for the technologies. For example, here we are miles away from. This is also higher. Here we are also not today. We are probably here a factor of 2 away. So that is it's questionable. We could argue about these things.
Excuse me.
Yeah.
2050.
Yes.
But so it's not taking into account climate change.
No. No, we don't have your data yet. If you give us your data, we're happy to put this into these models. If we could have access to this kind of data, we would immediately try it. I mean, that's just, it's always, I mean, the data question is always a question of accessibility, and we cannot do it ourselves. But we are happy, if you supply it, we are happy to do a study for that.
Here's a stick with them.
Yeah. No, that, we would like to do it, of course. So I will discuss this with you during dinner. Okay, what's coming now out of that is I like to show this picture here because we're doing this. It's an optimization model, and optimization models have problems. You have to always be sure that they are not really describing the reality completely. So what we do see here, you can't really read the legion. That's not so important actually. It's just the marginal cost of the different technologies. And what you see here is actually that wind would be, for most of the cases, the lowest cost. So the blue is wind, and the yellow is sun. But what you also see here, that's the red points, and this is just, and you have to be always very, very extremely careful when you work with these optimization models. This is just saying it goes at these points here. These are all the places where we can. It goes to 100%. So it's the constraints you put into your model which are really dominating a lot of the output. I mean, that's very, very important whenever you work with these optimization models, which are very, very tricky. So that's now the result, the result which came out of this, having the possibility to really distribute power over a lot in Europe. And being able to build also power lines more or less as you like. I will show you in a minute how big this power lines is. And again, you can hardly see what it is. So we have made here a lot of scenarios. I will just go through a few of it. That's the base. And the base is that most of the power would be supplied by wind. And you do see, for example, that solar and also solar thermal, this is solar thermal here in North Africa, play only a smaller role, much smaller than the wind. And we understand why this is the case, because this wind has this very nice smoothing effect. Yes?
In your optimization model, the objective function is cost, is
cost,
right?
Yes.
And the variables are the shares of the different renewables.
The variables are the installed capacities of the renewables. Okay. And then we take the time series, and from the time series we have to supply the power, of course. Yeah.
Is it for Germany or?
No, that's for this region here.
For the large region.
This region here, yeah.
It includes Northern Africa.
Yes, but it doesn't change. If you take out Northern Africa, it doesn't change the with the wind. Actually, that was the first surprise which came out, of course, is that also in Northern Africa, more wind is built than CSP. And there was one of the very interesting, it depends of course on the cost of the CSP, but it has also, we saw that we need to analyze this again with meteorologists. We saw, at least in the data we had, some different seasonality in North Africa than we had in Europe. And that makes it of course then extremely interesting for the model to take that, because then whenever you don't have to do something seasonal storage or so, that helps.
But do you quote somewhere the fraction now which is produced in Africa?
Yes, yeah, not in the report. I mean, I can send the report.
Where is it roughly?
It's not making a huge difference actually. We have also made this decoupled. We decouple it completely. and then it looks more or less the same. The wind is actually more it helps, but it doesn't make a huge, I mean
So it's a 10% effect.
yes, something of that order of magnitude. Yeah, it's not a. I mean, the advantage of going to North Africa is, of course, you have much more land where you could put, in principle, turbines and things like that. But it's not completely changing the picture. It changes only if you go to much CSP, because that you can only apply in North Africa. Now coming to one of the scenarios which I find are extremely important when we discuss actually within Europe, and this is actually this one here. In this scenario, we allowed nuclear to being installed, yeah? And now it depends, of course, pretty much, and we made no limitation, and we assumed costs, different costs. So here we assumed we would have nuclear at 3,000 euro per kilowatt, yeah? If that happens, you see nuclear takes everything immediately, more or less. You have still a little wind at very, very good sites. This is, I think, 4,500, and this is something like 6,000 euro per kilowatt. So even at a very high cost of nuclear, it would take a share. And I think that's very important, again, to see that, because now you can argue we will see in Europe countries which will stick to nuclear for quite some while, and we have to find a system where we can combine both things. If we don't build up systems in which we can combine, we will not have a European electricity market, or we will have a lot of problems. And having the strong network is actually the solution to this problem. Because again,
how many nuclear power, how much gigawatt would this correspond to? This large?
you can. I mean, that's something we're talking here about.
3,000. 3 times more than today, basically.
Yeah. Yeah. I mean, this is just an optimization model. It's
and
not.
Where's the Framatome price now? 3,000 or 6,000 for ECR?
I think you know better here. I think.
Depends where you build it.
In France, Framatome.
Oh, in France, the first one is going to be more expensive than this one.
Going to be, yeah,
Five.
5,000.
five something.
Yeah.
More
Yeah.
than
What's the
that.
other big
No,
one?
the first one is more expensive.
More than that.
Yeah.
You have another one that
Oh,
takes
yeah, 5 something.
But this is here. Then this is coal. This is coal. Yeah. But then you don't reach the CO2 emissions. Yeah. Okay. So, but just to come back to the interesting thing is if you have something, if the renewables supply such a supply curve, you can bring nuclear below that. So it's not a major system confrontation then. Yeah? I think that's very, very important. That's very important. A strong network makes systems compatible. I think of course, if you look now what capacities you need at interchange capacities between the different countries, this is, of course, depending a little bit on the demand, we're talking about huge network capacities, which is not realistic these days. I mean, it's unrealistic. Again, of course, we have to think a little bit about technology, whether technology, if we go to cables, if we maybe at some point go to something like superconducting high temperature cables, if that is a realistic solution. Today, it's certainly not, but at least we have to think about it. We have not to forbid it.
What's
So,
low demand, high demand? What's low demand?
that's the demand of the electricity within Europe. High demand is 4,500. Low demand is 3,000, as we have today. Yeah. Yeah. Okay, and that's again this low duration curve. So that's just. I mean, I think it's extremely important. I think that we're now doing these kind of studies much more in detail. So we're here. That's just the economic model behind it. Now we're building a very detailed electrotechnical model where we really map one-to-one these things, where we really want to see how the lines are built, and of course where we want to discuss all the other issues like how do you make the control of a system like that, which is not obvious from the very beginning. I mean, you have to imagine when you have only wind turbines, or what fraction of wind turbines which are probably which are not operating like a synchronous generator does these days, you have to think a second time about your control. And I think that is another issue, but I'm not going into that here. We might have some discussion about that. When we discuss about storage, I mean, we have to see what are actually our options, and of course the option which we do have within the power system these days is of course pump storage. So that's something which we know how to build it, but again it's extremely difficult from the acceptance point of view somehow. I mean, although I found pump storage when I see them in nature, usually at least I thought somehow it could be accepted, but it's difficult. I mean, we have 2 projects in Bavaria these days, which are, I mean, whenever you make a statement about pump storage these days, you're in the newspaper. I mean, if you want to be in the newspaper, you just have to tell a reporter something about, we need pump storage. Then you know this will be in the, and it's, so that, then we have, of course, other things. We have all these batteries, but I like to show it like here. We have to be very honest when we talk about batteries. Even when we come down to costs of something like €100 per kilowatt hour, and with lithium batteries we are miles away from that, we are still not in the range of the pump storage. So that's something which one needs always to keep in mind. In the building it's different. With the lithium we are higher, and lead acid is, of course, when we make life cycle assessments of that and all the resource questions, I think we should probably not go too much into this direction. And of course we have other options. So what we have done, again, we have made a rather refined model to understand how to build up the storage, and now we focus actually only on Germany. We have a model where we make the power plant planning, an intertemporal one, then we make a storage planning with very high time resolution, and then we have also a third model where we say which capacity do we need to keep all the safety margins that we want to have. And now we have again assumed some development like it will be in Germany, something like 80% renewables till 2050, and we ask ourselves which kind of storage would we need to keep that when we do not have this supergrid. And of course here is one of the results which came out. So we offered, of course, only a limited amount of storage to the system. So that's pump storage, that's adiabatic pressure storage systems, and that's hydrogen, where we first make hydrogen by electrolysis, and then we burn the hydrogen in a gas-fired power plant. So what you do see is, again, depending now, of course, on when the system, when we have a very high fraction of renewables, that's till a certain amount, when we have something 40, 50%, 60%, we do not need much storage, and then of course the storage need explodes. So that's something which you can see. Then we do see that there is always a certain mismatch between charging and discharging. That depends very much on the kind of renewables you bring into the system. And of course we do see that at some point we would need something like a seasonal storage. So that is, I mean, the unit here is a gigawatt hour. So here we are in the terawatt hour region. With our pump storage, we are today in the 40 gigawatt region. So it's much more than that, and this can only be done in a chemical way, like producing hydrogen. So what we have is, we have this technology here, we have the pump storage, we do not have this very efficient compressed air storage systems. I mean, people are talking about it. RWE is making this prototype, Adele, but whatever you hear from it, it's still not, I mean, there is a lot of issues with it. I mean, you need to have a very good high temperature store, you need to have compressors which work at these temperatures, and so there is a lot of engineering details, so that these things could be done. And of course, when we come to this kind here, when we talk about hydrogen, we are of course miles away from costs which are acceptable. I mean, as long as electrolyzers are in the range of 1,000 and more euro per kilowatt, everything like that is prohibitive. So we have to come down to costs of 400 euro per kilowatt per electrolyzer, and we're not there. It's still a good fraction away from that. Okay, so now storage is a possibility, but from the economic point of view, I mean, the technologies, we have a lot of these technologies, but it's not in a cost. Yes, that's only for Germany.
2050, how much electricity from renewables?
80%. We assumed 80%. And then you do see, especially that through the wind, we get a lot of the seasonality, and this would be then only be balanced with hydrogen. So that would be. I mean, again, we do see now with having more data that this seasonality is extremely difficult to capture for wind. Actually, one wind year is not like the other. For solar, it's you have a much smoother development. But wind is, we have two young PhD students have now tried to develop a seasonality index. And this is really varying from year to year. And that will make the economics of such a system very, very risky. 1 year you have some storage, and some you don't. Now I come to the more exotic things. Start power to heat or power to gas. So what we have, again, this is for Germany now. We only have analyzed that for Germany. So we have now connected the different systems. So we have the electricity system, as we had it in the moment. So we have the demand here. We have the heating system. We have also assumed the hydrogen. So we have some hydrogen demand these days in Germany, roughly 60 terawatt hours for various reasons. A lot of the hydrogen is used in refineries and in ammonia production. So these are the biggest, And so the idea is now we try to couple all of these sectors. So of course with gas we can heat, we can produce electricity. We could of course use electricity to make hydrogen, and then we could even make out of hydrogen gas through methanization. And so we have now really coupled all of these things within a model and try to understand what comes out. So the first result I like to tell you is whenever you have these two competing, most of it goes to the heat. Overproduction and so goes into the heat because that's much simpler being organized. We never saw in our model that we see that from some electricity makes hydrogen, but that then from hydrogen gas is made in a methanization stage. We never saw. We never saw that happen. We never could bring the model into this direction. Only very, very strong constraints.
Again, cost minimization.
Again, cost minimization. Yes. So this is we are very simple in that. Yeah. What you see is now, and I like just to mention this, is of course that you have now a quite interesting interference between the electricity system and the heating system. And what you do see is that Germany, I mean, we knew that Germany is split in two halves, that we have a southern and a northern part. But you do see it now here as well, because in the northern part, you see that in the northern part where you have a lot of wind, there is a tendency that electricity is in winter times used to make heat, while in the southern part, where we have more photovoltaics, CHP is more favored, because CHP is something which you need, which produces heat in winter when solar is not producing electricity. So this is very well matched. So you can, from this point of view, and I tell that always the Stadtwerke Greifswald, that they should stop working on CHP, because when the wind development goes on as it goes on these days, they will have a problem to run their CHP plants. and so they should switch everything to heat pumps. I mean, that's very simplified said, but of course, again, you can make this kind of analyses and see the differences. Now, the last few minutes, I will talk about what we call smart grid. Yeah. The first thing one has to keep in mind when we talk about smart grid is that many people like to talk about refrigerators and dishwashing machines and washing machines. But of course, the households are only responsible, at least in Germany, I don't know how it is in France, for 25% of the electricity demand. The biggest part is going into industry, and this is the service sector. So we should be very clear where we really try to make things now more flexible.
The peak times are just...
That's the overall electricity demand. It's in terawatt hours, yeah. So that's 200, that's 150, something like that, yeah. So again, we use now this first to get an idea about that. We use now this model we had for storage and brought in some flexibility into the demand. And you can learn some very nice things about that you can reduce now the storage demand actually quite considerable by demand flexibility. Actually, one of the biggest effect is if you have electricity heating. That really takes a lot of the overproduction. And I mean, that's a very, very rough estimate. Something like electromobility would also help if you have flexibility. You don't need to have vehicle to grid. You just need to have an intelligent loading station. That helps. So that is something which you need to keep in mind, that it helps, but you have to make it now realistic. So I show you now two examples where we are currently really working on to make the demand more flexible. And one is that we try, and we are working here together with Siemens, we try to make building automation systems more flexible to some price signal. So the rationale behind this is that we say, okay, before we bring smart home management systems into every household, we should look for a system where we have some automation already today, and that is in office buildings. In modern office buildings, we have an automation system which has access to many of the items within the building, and so we think it might be a good idea to start there. And what you need to do now is you need to really develop a lot of things which are not so simple. We need to have a mainly model predictive control system now. So we need to know how much heat do we need tomorrow, and of course, what you come up with, what you can use are things like your neural networks and so on. And this is actually what we applied. And so we have built such a system. But of course, when you look into this economics of that, for example, you see it's very, very difficult to make this economically attractive, especially if you look to the electricity prices and the electricities as we have it today. We see, of course, all these fluctuations of the electricity prices at the stock market, but this is never coming to the customer. Even if this fluctuation would be handed over to the customer still has more than 50% of a fixed price part. And so the question is, can this be made more flexible as well? Will we see some tariffs of that kind? And our experience these days is that this is more than tricky. And we have another project where we really have the grid operator and some people who offer some flexibility, and we now try to bring them together, and that's difficult. I just like to show another thing where we are working on, which I personally think will never be realistic. I'm sorry, that's in German. But it's just an idea on how things could be. So if you look into industry, you still have a lot of compressed air. A lot of the electricity demand in industry goes into compressed air, quite high number. And so the idea is that you make this compressed air more flexible by having maybe a second star where maybe your system runs at something like 6 to 8 bar usually, but you have a storage where you bring in now the compressed air to maybe something like 50 bar, and you run it from this. We're actually just building a test stand in the institute where we really want to show how things like that can work. We are working together with BMW to get all the load curves and so. And that might be possible. Again, if you look into the costs, it's not so obvious that it is cost competitive. And of course, you need to change a lot of things in your system. And of course, many people talk now about making that in households. I mean, in households, of course, we do not have any information infrastructure yet in place, which really can make the discussion between the refrigerator and the home management systems. We are also in a project like that. Actually, this is together with SMA, this inverter producer in BMW, and we will build a house now. We will build a house with all these gadgets, with an electric vehicle from BMW in front, where we really have then all these nice things. And I can imagine that some people are happy to have something like that. I doubt that it will solve these problems. It's more a luxury, green consciousness thing that you know that, and it's prestige, and yeah. We will see. And it's nice for a PhD student to build up the control of that. Actually, that's a nice point. This house will be built by a company making houses, and we are looking for a family at least for 2 years to live in the house. So that's actually one, no, not the student, one of our postdocs most likely will move into this house. So it's like that. Okay, I think I took my 45 minutes, so I like to come to the conclusion. I think that's very important. Larger networks are really making the integration much simpler, much simpler. Storage requires, I think, a better understanding of especially cross-sector couplings. I haven't discussed that now very much in detail, but whenever you have a cross-sector coupling now, for example, power to heat, this makes the economics of storage difficult. You really have to, if someone always takes the extra production when the electricity price is low, and that is something you need to keep very much in mind. And all these things about flexible demand, there is a lot of possibilities, and again, one has to study a lot of things, how flexible buildings really are. But we need very sophisticated prediction systems. And again, you have to imagine, we have then these hundreds of thousands of different suppliers, and then we have in many houses flexible demands. That becomes a rather complex system, also from the control point of view. And if you're afraid of NSA, you will not be happy with the information flows necessary to make these controls. Coming back to my introductory statement, I think we should see there are good ways we can really come to very high amounts of renewables. I mean, that is one. But we should, of course, on the other side, not discuss it too black and white. And I could imagine that in special cases, of course, we would be better off if we have a more hybrid system. And maybe, especially, I think that I like this here to come to this place here. I think it could be a very good German-French dialogue to bring up this system where more options than just the renewables are discussed. Thank you very much.